Another method for getting light interference is through what we call thin film interference. Okay, let me explain the situation. What we mean by thin film is if you have 2 or 3 media involved. For example, let's take the case of a little layer of oil that fell on top of a pool of water. Then the thin film is going to be the thin layer of oil, and our media are going to be air, oil, then water. Now another case would be like water on top of your windshield. Air, water, glass. These are the cases where we have a thin film. Now, what's going to make us get interference when we have a thin film? Like we talked previously, we have interference whenever 2 coherent waves travel different distances before they reach a particular point. Now, if when they reach that point, they are in phase, then we have constructive interference. If they are out of phase, then we have destructive interference. So the key is the path difference that the 2 waves or more waves travel. If that path difference is a integer multiple of lambda, we have constructive interference. If it is an odd integer multiple of lambda over 2, we have destructive interference. How does this happen in this case? Consider this light beam here that we are shining on the thin film. Now, once it reaches the thin film, that beam is going to be divided in 2. Part of it is going to be reflected, and part of it is going to move into the thin film. Excuse me. Now, the part that moves into the thin film, once it meets the third medium, part of it is going to be reflected, and part of it is going to move into the third medium. We are not going to worry about this one for this case. Let's worry about the reflected one. The reflected one, once it reaches the interface with the air, part of it again is going to be reflected, but we are not going to worry about that. And part of it is going to move back out into the air. Now, if we have someone looking at it, or a camera or whatever looking at the beams, that eye is going to get 2 beams of light that are coherent because they came from the same beam. Beam 1 or ray 1 and ray 2. Now, if these 2 rays are in phase, we get constructive interference. If they are out of phase, we get destructive interference. Now, ray 2 has traveled this extra distance more than ray 1. How much is that extra distance? Okay. For thin films, if we call the thickness of the film T, if the thickness is quite thin, we can approximate that path difference to 2T and say that ray 2 travels approximately twice T further than ray 1. That's one point. But that's not the end. Remember what happens whenever we move from one medium to another. Focus on the reflected wave. If you recall, whenever a wave is moving in one medium with a speed v1 and it moves into a second medium with a speed v2, if v2 is less than v1, the reflected wave is going to undergo a phase change, or it's going to flip upon reflection. If instead v2 is larger than v1, the reflected wave is not going to undergo that phase change. Also remember, N1 and N2, the indices of refraction, are a measure of the speed of the light in that medium. N is given by c over v. C is the speed of light in vacuum, v is the speed of light in that medium. So in other cases, in other words, if n2 is larger than n1, that tells us that v2 is less than v1, and vice versa. What this means, if we go from one medium where I have an index of refraction n1 to a medium n2, now if n1 is larger than n2, that means that the wave is going to speed up when it moves to n2, then the reflected wave does not have a phase change. If n1 is smaller than n2, that means that the wave is going to speed up when it's going to move into n2. That means that the wave is going to slow down when it moves to n2. Then in that case, the reflected wave is going to undergo a phase change of 180 degrees, or in other words, it's going to flip, or the wave itself is going to shift by an amount equal to lambda over 2. Okay, what does this translate to in terms of interference? Let's think of this in terms of the wavelength. The first wave, depending on the medium. So if we go from n here, air, to n1, or in general from n0, that can be anything, to n1, then the reflected wave is going to undergo no phase change or have a wavelength phase change, depending on the case. And there is no change in the wavelength due to the distance. Now, for the second ray, depending on the relationship between n1 and n2, there might be a phase change resulting in 0 lambda or lambda over 2, like we talked about in the previous screen. And then we have to figure out how many wavelengths are we going to fit in this twice t. Okay, the key here, we have to worry about the wavelength inside that film, because light is moving in that film now. So we cannot use the wavelength of light here. The wavelength of the light in the film is just equal to the wavelength of the light at medium 0 in the air divided by the index of refraction, n1. When the difference in these wavelengths is an integer multiple of the wavelength, we have constructive interference. Otherwise, we have destructive interference.